We're going to start now. So I'm Richard Jones. This is my colleague Eric Blake. We're both from Red Hat, and we're going to be talking about network block device MBD protocol. So MBD, network block device, it was added to Linux 22 years ago, 1997. Cast your minds back. It's very simple. On the left, we've got a server, MBD server, and perhaps that server's got an extra disk or a spare partition, and you want to make that appear on the client on the right as a virtual device, dev MBD 0. These two servers, you know, they're not virtual machines, they're real servers separated by a bit of Ethernet cable. So this very simple protocol was added to Linux. It has literally two commands, read a block, write a block, but you can use that to make this virtual device appear. So let's wind forward 22 years to today. We've got a few more commands, but it's still a fairly simple protocol. We have other things that aren't in here, like TLS support for encryption, authentication. We've got a few more servers these days, so we probably have about 4 or 5 servers that implement something like the full spec, and we have a similar number of clients as well. But you can still use it in the same way if you want. You can still have 2 servers. You can export a block, a disk from one and have it appear as a block device. But in the virtualization community as a whole, this isn't really how we use MBD these days. So I've got a few examples of how we actually use MBD. Here's my first example. We've got a QEMU virtual machine that's running. You can use these commands to take a point-in-time snapshot that appears as an MBD server served by QEMU, and you can connect to it, to your backup solution, and take a point-in-time backup from that. We have a tool called virtv2v. It's used to convert guests running on VMware and convert them to run on KVM. And to get access to VMware, we have to use this hideous proprietary library called nbdk. And for various legal and licensing reasons, we're not allowed to link it directly into virtv2v. So what we do is we link it into an MBD server, and then we're just using MBD as the protocol between these two processes running on the same machine. So it's a kind of a loopback MBD connection. Here's another example when we want to move workloads from different KVM-based management systems. So you've got things like OvertRev, we've got things like OpenStack, we've got things like KubeVirt, and we want to move those workloads between the systems. They all use different protocols to access their disks, and although we can use QEMU image convert to copy the disks from one machine to another, we have to use separate MBD servers to talking with custom plugins to those protocols. So in this case, we've got 3 processes running on the same machine, and we're using MBD over those little loopback connections. Here's another example. We've got Overt/Rev has got a component called ImageIO, which exports disks over HTTPS. But it uses the backend QEMU MBD, which is QEMU's MBD server. And the reason it's using that is simply because of the features of QEMU MBD. It can access block devices and QK2 files and many other types of systems. And again, 2 processes running together. MBD is running over a Unix domain socket between those. Here's an example, completely different one. Again, this is how you boot a VM, which is located on a web server, like a disk image on a web server, as XZ compressed. You can use this very long MBD Kit command to boot it without even downloading the file, without even uncompressing the file. Here's another example. MBD Kit isn't just about getting access to existing disk images. You can use it to create disk images from scratch. I've got a much longer talk about this, about writing block devices in shell script. If you look on YouTube, there's a talk called Better Loop Mounts with MBD, which I gave at FOSDEM in February. So what is MBD today? If you want to think about MBD, think about it as a universal protocol that you can use whenever you need to access a virtual machine, disk image, block device between 2 processes. And as 22 years ago, that might be 2 processes running on different machines. but it could equally be two processes running on the same machine. So now I'm going to hand it over to Eric, and he's going to talk about optimizing that particular copying case that we have between the different KVM-based management systems.
Thank you. Well, we know that QEMU image convert takes one disk image and copies it to another, but disk images are usually sparse. There's usually lots of zeros. So right now I'm going to create a disk image. 100 megabytes ought to be good. I'm going to stripe it. I'm going to put data every other megabyte, leave the other megabytes holes. So it now has 50 holes, 1 megabyte each. And I've written a little script, again using NBD Kit as our test bed. This script copies from my source over to an NBD destination. Right now I've got no zero detection. This is what state-of-the-art was QEMU 3 years ago. We copied the entire disk by reading the source and writing the destination. It took me about 8.5 seconds to do that, all with 400 writes. And we sat there and looked at each other and said, that's a lot of zeros. Half of my image is all zeros, and we just sent all of those zeros over the network. So what if we add a new command? NBD gained the write zeros command. Now all we have to do is send a single header, and the destination gets that header, and he can do a constant time operation, poke a hole in the file, and we've cut our time nearly in half, 4.5 seconds. Or maybe poking holes isn't efficient. We have a server that takes that short command over the wire, fills its own buffer of zeros, passes it to the right back end, and the back end, hey, 8.4 seconds, 8.5. We did save some time. We had less network traffic. So either way, we gained speed by adding the write zeros command. We looked at each other and said, can we do better than that? Let's add a block status command. We're going to ask the destination, do you already read zeros? If so, I don't have to write to you. And when the destination was already 0, yay, we're just as fast, or we gained a lot of speed with that slow server. And then we realized, oh, if the data is there and we do have to flush the data out to 0, we just doubled our I/O or added a little bit, or if block status itself is slow, ouch. Linux guys, tempfs file system, lseek seek hole is linear in the offset that you're probing, which turns a linear pass through the file into a quadratic copy. Ugh, we didn't like that. So QEMU image convert does not use block status, but the extension is used elsewhere in QEMU. We do like the extension, we just weren't able to use it for our copying. Then we said, well, if reading whether it's sparse is inefficient, what if we just make it sparse? So about 1.5 years ago, QEMU 3.1, if I'm remembering my versions, we added a pass where we said just blanket write the entire image to zeros and then go back and write the data in place. Hey, look, we got better. 4.5 seconds turned into 4.25. We shaved some time, because instead of having to write 50 1-megabyte holes, we just wrote the entire image. QEMU has a limit right now where it does 32 megabyte writes. We had a 100 megabyte image. 32 doesn't quite fit in without 4 writes. But fewer I/O over the network, bigger writes, we got faster. Or so we thought. Then we pushed it out to the users and we got reports, hey, my thing slowed down. What'd you do to me? And we said, well, it worked faster for us. Oh, you must have one of those servers that does not have constant time zeroing. It has the linear time zeroing. We went from 8.3 to 12.5 seconds because we're writing zeros and then rewriting the data. Double the I/O, double the time for the data portion of the disk. That's unacceptable. So we had to back that out in QEMU 4.0. But we looked at it and said, well, if we already knew that we don't want the slow pre-zeroing, but pre-zeroing did speed up the fast. What if we knew if there was a way, so this is backing it out, what if we knew if we were fast? Then we could get back to our fast constant time server and still not penalize our slow linear time server. QEMU added a new feature in 4.0, and we finally implemented it with NBD for QEMU 4.2 that's coming out soon. And when we use that feature, we can ask the server, are you fast? If it is, great. We'll finish zeroing the disk, 4 fast zeros, and we're done. We don't have to write any more zeros. Or we ask the server, are you fast? The server says no, but the server's answer is fast, so we didn't lose any time. Then we proceed just to write zeros on the holes, but 8.4 seconds, we didn't lose any time. So this new feature was added, as I said, with QEMU 4.2 coming out. We also added libnbd. That's our brand new user space library for connecting as an NBD client that we wrote this year. We also added an NBD Kit to a number of the existing plugins. The noticeable absence, the file plugin does not have this, and again, because the kernel folks, if you do fallocate to punch holes, you don't know if it's going to punch fast or if the kernel is going to be helpful and write zeros on your behalf slowly. If we could have another flag in fallocate or another flag with the ioctals to say, do this if you can do it fast, but error out quickly if you can't, it does help the pre-zeroing case. And with that, I'll give it back to Rich for some more fun we can have with the NBD Kit.
So Eric actually live demoed just then using MBD Kit. And MBD Kit is great for testing and for demoing because you can write your own plugins, or there's a whole ecosystem of plugins already for it that allow you to very flexibly write and test block devices. So there is like a million things I could tell you about MBD Kit. We'd be here all night, so I'm not going to do that. I'm just going to show you some really fun stroke stupid stuff that you can do with MBD Kit. So the first one's serious, the others are frivolous. I talked before about using MBD Kit with VDDK. What that gives you is an MBD endpoint, and you can connect a lot of different things to that. So let's have a look at actually what that looks like. So here I'm going to run MBD Kit, the VDDK plugin, and a local VMDK file. And that gives me this MBD endpoint. It's located at this URI. One thing we've standardized, as well as the protocol, is this URI specification. So I can now connect MBD SH. MBD SH is a little Python shell, and you can just type in basically MBD raw commands. This is the command to read the first 512 bytes, but it's also Python, so you can just use Python commands as well, and you can use loops and everything else you can do in Python. I can also, of course, connect libgestfs to an MBD endpoint, again using the same URI syntax, and you can see libgestfs has found that it's a Fedora 17 guest, and you can read it, even write it. And the last thing we can do is we can connect MBD Fuse to that endpoint. Now, MBD Fuse turns the MBD endpoint into a virtual file. What I've done there is I've created this MBD file. It's 10 gigabytes. It's a virtual file, and you can read and write to that file. And if you write to it, the writes get reflected immediately back into the VMDK file. So let's have a look at another frivolous thing we could do with MBD Kit. I'm going to create a directory on Eric's laptop here and put Busybox in it. What am I doing with all those commands? What does that look like? So that looks like a Unix file system. It's got a bin directory, it's got a dev directory, it's got sbin Busybox. Now what I can do in one single command is take that directory, turn it into an ext4 file system, put a partition around it, and give that to QEMU to boot. And there we go. And here I am in my Busybox-based virtual machine. When you have Busybox, you have to run this install command, which completes the rest of the Busybox install inside the VM. So now it's created all those commands from Busybox. Next thing I can do here, we have this concept called data disks. Data disks are disks which are quite simply specified entirely on the command line, on the MBD Kit command line. And the way you do that is by listing the bytes in the disk. At the end here, you'll notice there are 2 bytes, hex 55 and hex AA. I can see Kevin smiling there. But those of you who know about boot sectors will know that this is a bootable boot sector. And then using another MBD Kit feature, I can pass that to QEMU and boot it using the HDA option. So I wonder what this does. Interesting, huh? Do you think that's a trick? Do you think I'm really doing that? This is a demo by a very clever guy in Czech Republic called Jan Kadlec, who wrote this as a MS-DOS COM file in 256 bytes. It really is doing ray tracing as well. All I've done is to turn this into a boot sector. And on the similar sort of vein, here's another thing we can do. So this is a thing we call reflection. Now, MBD servers, they don't just serve one disk image, they can serve multiple disk images. And the way it works is that you tell MBD, the MBD client tells the server which disk image it wants to access by sending an export name. Now, using MBD Kit, we can abuse this facility and send the export name to the server, and then have MBD Kit send the export name back as a whole disk image. And the important point about this is it allows us to specify an entire disk image on the QEMU command line. So here I'm connecting QEMU, telling it to connect to MBD Kit, which is doing reflection, and then in the export name here, that's a base 64 encoded disk image. All of these examples come from Oscar Toledo Gutierrez's book about writing boot sector games. Here's one of them. Space Invaders, brilliant. You can actually play this game as well, so yeah, and you can fire as well. I've got another game. Because we're running out of time, I'm just going to very quickly show you one more game, and let's do this one. Dun, 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 dun. Yeah. You can get through the first pipe. That's terrible, isn't it? All right. I'll just finally hand you back to Eric to finish off. Thank you.
I don't have any games here. We want to use QK2 files with NBD. There are two options. We can say, take my QK2 file and parse it with my server into raw bytes, send those raw bytes over the network, take those raw bytes and hand those raw bytes to the guest. Or we can say, take my QK2 file, take those bytes as is, pass my QK2 file over the network, and then at my client, parse those QK2 bytes into the raw bytes seen by the data. Now, there's differences between them. One of them, if you pass a QK2 data to the client, then the client has everything QK2 offers. Backing files, you can change the guest size, bitmaps, you name it. Well, it has everything insofar as you have the space. We have this little problem where if the guest causes any action that needs to write a larger QK2 file, there's no pushback. If you didn't pre-size your QK2 file big enough on the source, the server says you're out of space and you're stuck. So 99% of our documentation right now recommends that you export raw files. With raw files, well, your guest can't resize. We want to mix those two. We want to have resize over NBD. So the next feature we plan on adding to QEMU, to NBD Kit, to all of these, is a resize feature. Now, in implementing this, we have to make some design decisions. Do we want it automatic, like a file system, where if you write beyond the file, then the server automatically resizes it to care for you? Or maybe we want it more explicit, like a block device. If you write beyond the end, you fail, but you can then use a resize command, resize it explicitly in band, or even with an out-of-band means, have the server do a resize behind your back, and then when you retry, now that it's bigger, it succeeds. We also have the NBD protocol. The original protocol always answered with a 16-byte structure called the simple reply. That gives you a yes or no answer. I did your command, or I failed with this error no, which isn't very powerful. So part of the additions we've added in the last 3 years was structured replies. It's part of how we do block status, but we would also use a structured reply for sizing. Then the server can answer and tell you, I also have these additional 8 bytes, and that's the new size that I'm actually using. So if the server rounded your request size up, or even if you could say, resize me with a delta of 0, then the server can tell you, and here's your current size. And that structured reply has some cool features. Normally, when you send a command, the server replies back, and the transaction's done. you don't get any more information. If the server can change the size behind your back, such as an LVM image, then that means your client has to poll, send a new command every time I want to say, what's your size, what's your size? Oh, you grew, finally. But it would be nice, we could say, I want to set a notify bit and create an open-ended command. Then the server replies and says, I have a new size for you using the same handle that you started, but I have not finished the command. This command remains open, and then down the road, 10 minutes, 10 days later, you resize again. The server passes another reply. Could be the longest lived reply out, or command out there, but you've turned this polling into a notification loop. So there's some great potential for what we add in the resize command. And we're sitting there saying to ourselves, do we want all servers to implement the latest and greatest and give us this notification loop? Well, it comes at a cost. Servers are more complex when they have to do a notification loop. Having an open-ended command ties up one of your threads if you have a threaded server. Or if you don't have a threaded server, if everything was in order, you can't even do it. You have to become a threaded server. So we may need more knobs. We may need to have some handshakes where the server says, I'm willing to offer this, but not that. And the client says, oh, OK, I can deal with that and fall back where I don't have it. But it makes the clients more complicated, makes for more interoperability testing. So either way, we're going to have some fun with the design. You're welcome to contribute on the lists. But we are going to be adding resize. And with that, I hope we have a good summary. NBD is a simple yet flexible protocol and has lots of uses in virtualization. Do we have any time for questions, or is this the end? We have time for questions. You want to see Rich do better on FBird.
I have one silly and simple question. For the game code you showed in the demo, is that code open source? Is there any copyright concerns?
So all of the demos I showed, they are source available, but they're not open source in the licensing terms. However, they do all, I mean, all of them actually, including the ray tracing one, come with full commented source codes, and they're quite interesting to read. Obviously, this book is the source code for this second lot of demos.
Okay, so thank you.
All right, thanks for your attention.